as all panelists. Today's speaker is Dr. Shuhua Hu. Dr. Hu is a research scientist at Certara. Before joining Certara, she worked at the North Carolina State University for a decade with a research focus on mathematical modeling in the area of biomedicine and engineering. Shuhua earned her doctorate in applied mathematics from the University of Louisiana at Lafayette. She has published over 30 peer-reviewed journal publications. Shuhua, welcome to today's event. I'll now turn it over to her to begin the presentation.
Okay, thanks, Suzanne. Thanks, everyone, for attending this webinar. Okay. Now, in this presentation, first I will give a background and a motivation on using DD differential equations. Next, I will give a brief introduction to DD differential equations. There are roughly two types of DD differential equations. One is discrete DD, and the other one is distributed DD. So we will cover both of them in this presentation. Then we will discuss the relationship between the distributed DD approach and the traditional method to model DD outcome in PK and PD studies. Then I will explain how to implement discrete and distributed DDs in PML and demonstrate them with some examples. I just want to point out that the discrete DD is already available in Phoenix 7.0. Now for the distributed DD, we just add this feature inside Phoenix. You cannot use it now, but it will be available in the future Phoenix release. Finally, I will conclude this presentation by some summary remarks. Now, why modeling DD is important? As we know that most process does not happen instantaneously. For example, delays may arise from the PK absorption phase, as shown in this figure. This is because it takes time for the drug to be transported from the depot site to the central compartment of drug administration. And the drug effect may be also delayed with respect to drug concentration at the central compartment, as shown in this figure. For example, a prodrug may need to be metabolized to the active drug before response is observed. Now, traditionally, transit compartment models described by this system ordering differential equations have been widely used in the literature to describe the DD outcome in PK and PD studies. For example, they have been used to model PK absorption delay, while the last compartment is the input function feeding into the central compartment. They also have been used to model delayed anti-cancer drug response, with the last compartment denoting the delayed drug effect. The obvious disadvantage for this approach is that one needs to manually find a proper value for the number of compartments. It may also require a large number of differential equations to fit the data. In addition, it may not be adequate to describe some complex features such as double multiple peak phenomena after oral administration. Now here we will introduce how to use DD differential equations to model the DD outcomes. And as we shall show later, that this approach does not suffer this disadvantage. Now I just want to point out that DD differential equations is not a new concept. Actually, it has been widely used in bioscience and engineering to model DD outcomes. The original motivation for studying DD differential equations came from the applications in feedback control theory in 1940s, such as steady shift stabilization and automatic steering. So the feedback control means that adjusting the system to its desired state based on its current state value. But we know that when this information transmitted to the sensor, it always takes time. So what actually adjusts is based on the past value instead of the current value. Now, due to this delay, it's likely that you either miss the goal or overshoot the goal. So this is the system that you actually get how this oscillating behavior. Now, I just want to point out that this feedback mechanism is not limited to engineering applications. Actually, in human body, there are many feedback mechanisms trying to work to maintain the key physiological variables within the normal limits. For example, the heart rate and the blood pressure control is mediated by various neural and hormone mechanisms, and each mechanism has its own delay time. That's why you see a heart rate and blood pressure have this oscillating behavior. Now, what about the biological application? So even though the biological application of DD differential equations dates back to 1920s, when Waltara tried to investigate predator and prey interaction dynamics, but the momentum did not pick up until 1970s. Now, until recently, the DD differential equations appear in the PKPD literature to model the drug-disease interaction. Now, this paper gives an excellent overview on this topic. Now, I just want to give a brief introduction to the discrete delay approach. Now, first we need to understand the difference between ordinary differential equation and delay differential equation. Now, for the ordinary differential equation, the rate of a change is dependent on the current time value and the current state value. But for the delay differential equations, the rate of a change is not only depends on the current time, the current state value, it also depends on the path value. Now, since it depends on the path value, you have to specify its path value. That is t less than or equal to 0, but less equal to greater than equal to negative tau. Now, this delay tau here is called a discrete delay. Now, the tau must be a positive number because you only know the past. You cannot know the future. Now, the differential equation involves only discrete delays are often called discrete delay differential equations or differential equations with discrete delay. And this S0 is often called history function. Now, here I just want to give a specific example on how to use discrete DDEs to model HIV dynamics. Now, this figure shows the basic pathway for infection and production of HIV for infected CD4 T cells. The basic when the virus enters into the host cells, it needs to lose the capsid and integrate with the host DNA and then transcribe into multiple RNA copies, and then assembling itself, and then bud out of the host cells. So we see that there's a delay from the initial infection to the viral production. Now, if we assume that the length of time from the initial infection to viral production is the same for all the infected CD4 T cells, then we can use this delay differential equation to model the free virus compartment. Here we have the free virus, and the S denotes the acutely infected CD4 T cells, and the N we denote the viral production rate. So here this term denotes the loss of virus due to the natural clearance, and this denotes the loss of virus due to infection. Now, just as said, the assumption made in the about HIV model is that the length of time from initial infection to the viral production is the same for all the acutely infected CD4 T cells. We know that in reality this is not true. Now, how do we accommodate the fact that the delay time may vary among infected CD4 T cells? Now, one way to do that is to use a weighted average of all the possible values for the delay time. Now, for example, if we assume that the delay time for 20% of infected CD4 T cells is tau 1, and the delay time for 50% of them is tau 2, and the delay time for the rest of them is tau 3, then the sum of all these discrete delay terms is the number for totally infected CD4 T cells that it can generate the virus at time t. Now, what if you have infinite possible value for the delay time? Then this sum just becomes this integral. Now here is C, denote the probability density function of the delay time, and they often called delay kernel. And this term is called distributed delay because there are distribution involved here. Now, if we use distributed delay approach to model this HIV dynamics, then we simply replace that discrete delay term by this integral term. Now, since now it depends on all the path value for S, so you need to define its value for t less than or equal to 0. Now, differential equation involves distributed delays are often called differential equations with distributed delay. Now, you may wonder if there's any relationship between distributed delay and discrete delay. The answer is yes. Now, especially if you consider the delay kernel T is a direct data function, also called unit impulse function, given by this one. So in this case, we said that delay is point distributed. Now, by using the property of the direct data function, you can easily find that this distributed delay term reduced to this discrete delay term. That means that the distributed delay approach includes the discrete delay approach as a special case. Now, how to use this distributed delay approach to model absorption delay? Now, in this case, St denotes the amount of drug administered at time t. For example, if we administer a single drug bolus at time 0, with D denoting the dose administered, then St equal to D multiplied by this direct data function t. Now, D denotes the PDF, the delay time between the administration time of the drug and the time when the drug molecules reach the central compartment. Then this script S, described by this discrete delay, is the input function feeding into the central compartment. Now, for example, if we assume that the drug can be described by one compartment model with a first-order clearance rate Ke, then the amount of drug at central compartment A can be described by this differential equation. Now, in the case where the St equal to D multiplied by direct T, then the above equation just reduced to this simple equation. Now, if we assume that G is a PDF exponential distribution, when you plug in, you will see that this equation just becomes the first-order absorption model. Now, how to use distributed delay approach to model multiple peak absorption profile? Now, we know that in some cases, after oral administration, the plasma concentration exhibits a multiple peak absorption after oral administration. For example, this figure shows that it has a double peak phenomenon. Now, one explanation for this phenomenon is that there may be multiple distinct sites of absorption. Now we just into how to use this distributed approach to this multiple pathway scenario. Now, if we let Sj denote the amount of drug administered for the J pathway, and the Jj is the PDF of the corresponding delay time, then the sum for all the script Sj is the input function feeding into the central compartment And this script Sj, it is defined by this distributed delay term. Now, how to use the distributed delay approach to model delay drug effect? And in this case, S is used to describe the drug effect. And script S is the delay drug effect. Now, for example, if we assume that the drug receptor binding is rapid, then S may be described as static function, such as the Emax model, given by this one. Then the resulting delayed drug response is simply this distributed delay term. Okay, now you may wonder if there's any relationship between transit compartment models and the distributed delay approach. The answer is yes. Now, if you assume that the delay kernel G is a PDF of gamma distribution with the rate parameter kappa and the shape parameter be a natural number n, now in this special case, we said this distribution is an Allen distribution. Now you can show that this discrete delay term reduced to a transit compartment model with this script S equal to the last compartment. Now from here you see that the shape parameter n determines the number of compartments, and the rate parameter kappa determines the transition rate. And the mean of this distribution, the ratio of n over k, is the mean transit time. So instead of writing a large number of differential equations, you can just simply use this simple integral to replace it. Now here I just want to give you a visualization on the gamma distribution. So here I plot the PDF of gamma distribution with the same rate parameter value, but with different shape parameter value. Now this red curve is obtained for shape equal to 1. In this case, it's just that it's exponential distribution. Now this green curve is obtained for shape equal to 2, and this blue curve is obtained for shape equal to 4. Now you see that with the same rate parameters, the larger the shape, the larger the variance. And so far, we have demonstrated that the distributed delay approach includes the transit compartment models, the discrete delay approach, and the first absorption model as special case. Actually, there are a large number for other models. It's also a special case of the distributed delay approach. For example, for the basic indirect response models with production either stimulated or inhibited, it assumes that delay time is exponential distributed. Now for the absorption model proposed in Savick and Shen, it assumes that the delay time is gamma distributed. And for the mixture of first order and zero order absorption model, it assumes that delay in the first pathway is exponential distributed, while the delay in the second pathway is point distributed. Now for the parallel input approach proposed by Godfrey for modeling WP phenomenon, it assumes that the delays in both pathways are Allen distributed, but with possible different shape and rate parameter values. I just want to remind you again that the exponential distribution is a special case of gamma distribution with shape parameter being 1. Allen distribution is a special case of gamma distribution with shape parameter being a natural number. Now, I hope that I gave you enough motivation and start thinking about using delay differential equations, and you began to wonder how to implement these different delays in PML. Now, here is the syntax for the discrete delay function. So this function returns the value that expression had at time t minus tau, and it gives the value 0 if t less than tau. So basically, this function can be used to determine the value expression had in the past. For example, the expression can be a state variable, observed variable, expression that depend on these variables, etc. And this delay function can be put on the right-hand side of the differential equation, and hence can be used to numerically solve discrete DDEs. Now, I just want to point out that in the case where the history function is 0, one can directly use the delay function to numerically solve the DDEs. However, in the case where the history function is non-zero or non-constant, you need to do some special treatments. Basically, you need to replace the discrete delay term with a corresponding history function for t less than or equal to tau, and then use the delay function afterwards. Now, it was pointed out that there's no restriction on the number of delay functions that you can put in a model, and the delay time tau can be estimated. Now here I just want to show you how to use this discrete delay function, solving the discrete DDE with history function being 0. Now this example is based on example 2 in Couch. Now where in the discrete DDEs were used to describe dynamics of proliferating tumor cell TP and apoptotic tumor cell TD. For this example, it includes the first order absorption model, and for PD, it uses basically to describe dynamics of TP and TD. Now for the TP, it is described by this alternate differential equation. So basically, this one describes the growth of proliferating tumor cells. And this term used to define the effect of the drug on the proliferating cells. And for the TD compartment, it is described by a simple left span model. So basically here, this tau d denotes the left span for apoptotic cells. So for the TD, it depends on the path value C and the path value TP. So you have to define the history for the TP. Now here it is given by 0 for this example. Now for the PK parameters, there's no individual variability, and the value of fixed effects are assumed to be fixed. And for the PD parameters, assume them all log normal distributed, include this delay time tau d. And the residual error model is a proportional error model. Now, just want to give you a quick demo of this example. Okay, this is the data that I'm going to fit that model to. And here I use the QRPM engine to do the estimation. Since it takes some time to do that, I just show you some of the results. So basically, after finishing estimation, Phoenix will automatically output all the diagnostic plots for you. And here is one of them. Now, Phoenix also output the estimated value for fixed effect, omega value, and its confidence interval, etc. So here's the estimated value for fixed effect. Now for the PK parameter, because they are fixed. Now for the PD parameter, now you see that there are some negative value here. That's because I use a log transformation to make sure that all the parameter value to be positive. Okay, now here is the model, the PML code for this model. So basically, we have a PK model described by first order absorption model. Now this is your tumor growth model here. Now for the TD, as we said, it depends on the path value C and the path value TP. So you simply use this delay function to do it. Now here, just specify the initial condition for TP and TD at time t equal to 0. And this is your PK parameters, and this is your tumor growth model parameters, and this is your residual error model. Okay. Now here, I want to show you how to use delay function to numerically sort discrete DDEs with non-zero constant history function. The example used to demonstrate is the so-called Hutchinson equation given by this one. And R here denotes intrinsic growth rate, K denotes carrying capacity. So we see that if there's no delay here, then this is basically a logistic growth equation. So that's why this equation is also called discrete delay logistic equation. Now here I just want to give a brief historic background on this equation. So this equation was proposed by Hutchinson in 1948 when he tried to explain the population oscillating behavior exhibited by the daphnia. Now this equation had an enormous impact on modern population dynamics with delay differential equations. And almost every introductory book on delay differential equations talk about this example. This is due to the fact that it can generate more rich and complex dynamics than its corresponding ordinary differential equations. Now to just give you some visual idea on what I'm talking about, I plot these Hutchinson equations with different delay time value. Now here this red curve is obtained for time equal to 0, so that's the logistic equation. So you see that at the beginning it grows exponentially and then reaches plateau value. Now this green curve is obtained for tau equal to 4. So you see that at first it has some oscillation and then it down reaches plateau value. But if we further increase the delay time to 8, now you see the oscillation is just sustained here. So by just varying the value of the delay time, the oscillation can become either damped or sustained. So one of the goals in engineering application is to try to change the value of the delay time to obtain the desired type of oscillation. Now here I just want to show you how to implement this in PML. Now since the history function is non-zero, so we need to use the conditional statement to achieve this. Now here's the way to implement the conditional statement in PML. Now with this, you can implement the Hutchinson equation in PML as this one. So basically at t less than equal to tau, you simply plug this history function inside here, as we got here. Now after that, we use the delay function to do it. Now here just specify x at time t equal to 0 is 0.5 here. Now simply you can use the same trick to use delay function to numerically solve this discrete DDE with non-constant history functions. Now still for this Hutchinson equation, if the history function is given by this exponential function, you can simply, at t less than equal to tau, you just plug this one inside here, so you get this one. Afterwards, you use the delay function to do it. Now from here, we see that at t equal to 0, this x is just equal to 1, so that's why you get here. Now, how to implement the distributed delay in PML? So, basically, the syntax for distributed delay is given by this one. It just extends the discrete delay function by incorporating another two options inside. One is your shape, another one is height. So this function returns the value of this integral. Now the delay kernel G is a PDF gamma distribution with the shape parameter being specified by the shape option, and the mean specified by here. Now recall that most of the commonly used PK/PD models for modern delayed outcomes assume that the distribution of the delay is either a gamma distribution or special case of a gamma distribution. So that's why we build this gamma distribution inside. In the future, if there's a need for other distribution, we will do that too. So the height option specify the history function for your expression. Right now, the history expression must be independent of time t, but it can depend on the covariance, fixed, and the random effect. And the his option can be used with or without a shape parameter. This means that one can now directly use the delay function to numerically solve discrete DDEs with non-zero constant history function. Now, again, this distributed delay function can also be put on the right-hand side of differential equation. That means that it can be used to numerically solve differential equation with distributed delays. In the case where the delay kernel t is a PDF gamma distribution and the history function is a constant. Now, again, the delay you can put in any number for distributed delay function in a model, and the mean delay time can be estimated, and the shape parameter can also be estimated. Now, just now I showed that I talk about that with this recent add option hit, you can now directly use the delay function to numerically solve discrete DDE with non-zero constant history function. Now, for example, for this Hutchinson equation, instead of writing this multi-lines code, you can just use this one simple code to do it with this hit option included inside. Okay, now just talk about how to use this. I want to show how to use the distributed delay function for the differential equation with distributed delay. Now, for this example, for the PK model, it describes a first order absorption, and the PD model is used to describe drug-mediated tumor growth inhibition. Now, here just use to describe the growth of the tumor cells. This term just used to describe the drug-mediated tumor cytotoxicity on the tumor cells. Now, this S is defined by this Emax model, and the delay kernel T is assumed to PDF gamma distribution with the shape parameter mean respect given by shape param and the mean transit time. So I just want to point out that if there's no this term here, this is just a Gamper model. So the Gamper model has been widely used to describe the tumor growth dynamics. Now, again, for the PK parameters, for simplicity, I assume there's no inter-individual variability, and the Y for fixed effect are fixed. And for the PD parameters, all of them are assumed log normal distributed, includes the shape param and the mean transit time. And the residual error model is a proportional error model. Okay, so I just want to do a quick demo for this example. Now, again, just want to point out that this Phoenix is a development build. You cannot use it now, so it will be available in the future release for this one. Okay. Now, so this is the data that I'm going to feed this model to. And again, I use the QRPM engine to do the estimation. So here again, I just show you some of the results. And here is one of the diagnosed plots that we get. So again here, to ensure that all the parameter value to be positive, I use log transformation. Now, if you want to transfer it to the original scale, you can use a secondary command to do that. Basically, this shows you, okay? Now, here it shows that the mean transit time is about 30, and the shape parameter, the value is about 4. Now, I want to show you the PML code for this model. Again, this is the PK model, and this is the PD model. Remember, we have this the distributed delay inside. So here we use the delay, Now you have a shape defined here, option defined here. Since the history is 0, I just put 0 there. So you just simply plug inside for the TC compartment. Okay, you need to specify the initial condition for TC at time equals 0. And these are PK parameters. And these are PD parameters. And these are the residual error model. Now this second, but I just said that I use secondary to transfer the fixed value from the log scale to its original scale. Okay, now I just want to do some summary remarks. Okay, compared to the traditional method, the distributed delay function in PML provides a more simple and flexible way to model delayed outcomes. For example, users only need to write one simple statement instead for a large number of differential equations to model the delayed outcomes. It also allows users to estimate the shape parameters along with other parameters instead of manually find a proper value for the number of compartments. Hence, it's more efficient and less error-prone. In addition, it allows the value of the shape parameter to be varied among individuals, and hence provide more flexibility for population analysis than transit compartment models. It also allows for non-integer shape parameters, and hence may capture the dynamics better than the transit compartment models. It requires for integer shape parameters. Okay. Now, if you want to know more about delay differential equations, here are some references that you can look at. Okay. Now, thank you, everyone, for your attention.
Okay, thank you so much, Shuhua. We'd like to invite our audience to submit your questions in the Q&A panel for Shuhua. Looks like we have our first question from our audience. Can discrete and distributed delay functions be used for individual analysis?
Yes, so basically this delay can be used for both individual and population analysis.
Someone would also like to know, is the tau function similar to the m-time function in non-mem?
It's a little bit different. Yes, this delay is used to numerical solve the delay differential equations. Yeah.
How were discrete and distributed delay functions implemented in Phoenix?
Okay, actually we have prepared some slides for that. I will turn this question to Dr. Mike Donnelly, who developed these two functions inside the Phoenix. Okay, Mike, can you do that?
Sure. Let me see. Have I shown the first picture now? It's slide 30.
Yep.
Basically, here's the simple discrete delay. We just keep a history of past values of the value that we're going to take the history of, and here it's shown in reverse time order. So time 0 is on the left, and we have something that's going up and then down, and then there's another dose, and it comes down again. And so we're looking into the past here, and so t, the current time, is on the left, and tau is some positive number that extends into the past. And so for a simple discrete delay, we just do an interpolation on the past data in order to get the value. Does that answer that question? I'll go into the distributed delay on the next slide if people want to know.
Go ahead and talk to that, Mike.
Okay. Essentially, this we're relying on the fact that the differential equation solver takes smaller steps during the period of rapid movement of the trajectory of the system. So at the moment, I'm using just linear interpolation between the states that are captured. And it's called on every derivative evaluation. So if it appears on the right-hand side of a derivative statement or an assignment statement, it may have a significant performance impact, so we have to use it sparingly. Let me go to the next one involving distributed delays. When we have a distributed delay, we assume that the delay is not a single number. It's instead a distribution, and we're using a gamma distribution. So again, now is on the left, and past time is on the right. And what we want to do is, rather than pick a single number off of this curve, what we want to do is convolve it with a gamma distribution. And this is how we do the convolution. We take the gamma distribution, we take the area of it between two of the time points that are recorded, and multiply it by the average value that the system had at that time. So you see the system had at that time. Can you see my mouse pointing at one of these buttons? It's
no.
Okay. Well, anyway, you see this gray slice, and there are two little circles representing the values that the system had in its trajectory going between those two time values. And so we assume that the middle value was used during those times, and we multiply it by the area of the gamma distribution within those within that time slice. And essentially what that means is that we get, since the gamma distribution is has a peak, we're getting a higher representation of the values at the time of that peak, but we're also getting quantities due to values at other times. And that's kind of how it works. The history table is considered as a series of step functions or a series of rectangles, and those heights are multiplied by the corresponding interval under the gamma density function. So I'm sure that's clear as mud, but let's see if people have any more questions.
Okay, great. Thank you, Mike. Someone would also like to know, how do we explain different shape parameters between individuals? For example, in vitro in vivo correlation models have to assume one model with a shape. Doesn't it require using more discretion before fitting different shapes for individuals?
Okay, I think this is just like different individuals. Individuals are different, right? Just like we may have different clearance rates. So the delay time, as I said, is maybe vary among individuals. So here we just want to give more flexibility to do that. Of course, you can fix this shape parameter for all the individuals. You can assume there's no inter-individual variability between them. So yeah, I think you can just assume there's no inter-individual variability if you think all the individuals have the same shape parameters. Yeah.
How does implementation of delay differential equations in Phoenix compare to solvers used in other software such as MATLAB?
So I still turn this question to Dr. Mike Donberry, who implements this delay function in Phoenix.
Okay, there are many ways to implement delay differential equations, but so we chose the most general one here, which is to essentially keep a history table. Now, what you do with that history table is, if you want the value of a particular variable at a time in the past, you can use various interpolations on that history table. So we're using linear interpolation because the time points are quite close together, and we have discontinuities, because every time there's a dose, or every time, say, a sequence statement wants to change some value, or every time there's say if you have an enterohepatic reflux, you have a discontinuity in the behavior of the model. If you try using a higher order interpolation across such a time point, you get crazy answers. So, so for the moment, at least, we're sticking with linear interpolation between time points. Does that answer the question?
I think so. Okay, thanks, Mike. Looks like there aren't any more questions from our audience. I'd like to thank our presenter today, Dr. Shuhua Hu and Dr. Mike